This week, we're going to finish talking about the statics method for developing influence lines, and then that'll be today, really. And then on Friday, I'm going to show you applications of influence lines. So once you've created an influence line, what do you do with it, and how do you use it? Then next week, we will go through a different way of constructing influence lines. This is the Mueller-Breslau principle, and this is the one that I said, once we get to this point, it's okay if you want to go lean on some online resources, but please refrain from doing that until we get to the Mueller-Breslau principle. And even then, I would use caution. I've seen some students be confused by different things that they've found online related to this. So I highly recommend just sticking to the lecture material, class content, the textbook, and then come see me if you have questions. Next Friday, we don't have class in observance of Veterans Day. So your homework 8, homework 8 on snow loads is due next Monday. And then homework 9, I will assign this week. It will be due the following Monday. Homework 9 will cover all of the influence load lectures, right? So there will probably be at least one problem where you have to apply influence loads, and then a couple problems where you have to develop influence loads. So that's going to be it before Thanksgiving, and then after Thanksgiving, there will be one more homework assignment due, and that last homework assignment will be on approximate analysis. So those are the topics we're going to cover the week right before Thanksgiving break. And these lectures are also going to be directly linked to the final project for this class. All right, so after Thanksgiving, we'll start talking more specifically about the final project. And then the last week of class, you have the third exam. So that exam will probably cover, it'll probably cover through homework 10 material, so through approximate analysis. We'll talk more about that when we get closer. And then after that exam, we have a few final lectures on finite element analysis, time permitting. Usually I get through at least one of those, maybe two, so we'll see. And then the last week of the semester, right, finals week, since we don't have a final exam in this class, we're still required to meet during our assigned time. So that time is 8 a.m. to 9 a.m. or 9:50 a.m. on Wednesday, December 13th. We will not have a final exam, but there will be a few things that I will present, that I'll have prepared, and an extra credit opportunity is built into that. So please plan on showing up. And then, yeah, we're really coming down to the end of it, almost at the final stretch. Yes?
So are we not tested on frames then?
Right. This will not be something that you are tested on. Think of it as a bonus lecture. Yeah.
When would we be able to retake our post exam?
Right. So after exam 3 is returned, and I do that pretty quickly, quick turnaround for exam 3. I'll start accepting submissions. So, I mean, really, if you know that you want to submit for exam 1 or exam 2, you can start doing your corrections anytime. It's just once you get exam 3 back, you'll know which one is your lowest, right? So after exam 3 is returned, that's when I will start accepting corrections for whichever exam you choose. Yeah, and I'll provide more details on that as we get closer to, in case you want to start doing corrections for exam 1 or exam 2. Yeah, good question. Any others? Okay. Good deal. So, quick recap. Last time we looked at this example of a simple beam with an overhang, right? Here's the configuration. and developed the influence lines for reactions at A and C before this page. And then here we started focusing on internal force influence lines, so specifically the shear and moment at B. So we went through that approach using statics and then made a couple of observations. And so now we're going to show you how to identify what are the important locations to place a unit load when developing influence lines. Because so far we've been talking about this in the context of, okay, we have a unit load on the beam, right? And we are marching it in this example. We did 10-foot increments. So it was here and then here and then here and then here. All right, 10-foot increments along the length. But we don't necessarily need to use or to calculate the reactions and responses for all of those locations of the unit load. So now I'm going to show you how to identify the key locations where you need to consider the placement of the unit load in order to properly develop a complete influence line. So this will cooperate here. All right, so we already talked about how determinate structures, regardless of the type of response that you're drawing an influence line for, that influence line will always consist of straight line segments. With that information, and you observed how in this previous example, right, we got some values, plotted those points, and then connected those points with straight lines, right? And here I said the slope is constant on this segment, and over on this side it's the same as it is on this side for shear. That's always going to be true at the location of interest where you have a discontinuous value. The slope is going to be the same. So you can think of it as just taking the same slope and then breaking that value apart, right? With moment, right, a moment influence line at the location of interest, which is B, the slope will change for the influence line, but the value will stay the same. But at every other location, right, in both of these influence lines, there's no change in slope or value. So, or I should say there's no change in slope at a specific point and no discontinuity in the value either, right? Just at this location of interest for shear. So really, we could have drawn these influence lines without knowing this point, right? Because all we need are these 2 points to get this straight line, and all we need to get this straight line are these 2 points, right? But we also need the location of the supports, right? That's always going to be important because we need to know where that value is going to be 0. And then similar over here. So with that information, all right, for any type of response, the key location, right, which is the location where you place a unit load, that's this value X in the brackets, would include each support, all right, any hinges, if there are hinges present, any free ends, if there are free ends, and that, again, these 3 characteristics identify a key location for any type of response. If your response is a reaction force, then that's all you need to think about, right? If your response is a shear force, you also need to consider placing the unit load immediately before the location of response. And I also sometimes call this the location of interest. And immediately after All right, so I'll make a note here that the location of interest, I'll abbreviate it later as LOI. That is the location of the response. Which is the same thing as, no, sorry, not the same thing as X. X is where you place the unit load, right? For moment, in addition to these three considerations, you also need to place the unit load at the location of interest. All right, so that leads us to write down a couple of rules that will always apply for influence lines. So if you're drawing the influence line for shear force, all right, at the location of interest, you're going to have continuous slope. All right, that's what I pointed out in the previous example. The slope stays the same on both sides of the place where you cut the beam. And you're also going to have a discontinuous value. When you're drawing influence lines for internal moment at the location of interest, that influence line will have a discontinuous slope. But the value will be continuous. And whenever you're drawing influence lines for a reaction force at the location of interest, that influence line will have continuous value and continuous slope. Now, the only exception to any of these rules is specifically for shear force if the location of interest is at a hinge. In that case, the slope of the shear influence line will be discontinuous as well as the value, right? So I think there is an example on D2L, which I don't know if I've posted it yet, but there is one example that demonstrates that. So that's kind of a weird situation, and it's not one that I would really focus on much in this class, but just keep in mind that is the only exception to these rules. Okay, any questions so far?
Will the value at a hinge also be discontinuous?
In this, yeah, for shear, yep, it will, yep. Any other questions? Okay, so on D2L, I don't think this is included in your skeleton notes, this page here. On D2L though, I think I called it the force or shear and moment challenge or something like that. So remember that all of this information that we're gathering to develop influence lines is information that you already know how to obtain, right? We're just using statics to get reaction forces and internal shear, internal moment. So it's easy to obtain that data. The challenge with this topic, influence lines, is understanding how to convey that information in the context of an influence line, because it's kind of reverse and inside out and upside down of what you're used to with shear and moment diagrams. So the challenge here, if you're interested and For some folks, this may lead to more confusion. For others, it may lead to greater understanding. So this is why I just put it on D2L in case you want to dive into it and explore it. This is going to kind of demonstrate for that same example that we just looked at before, the simple beam with an overhang, and various placements of unit load. What are the shear and moment diagrams for each of those conditions, all right? So we had 3 locations of unit load there that were not directly over a support, right? And as we talked about, if it's directly over a support, everything's going to be 0 except for the reaction at that support. So for those other 3 locations that will generate internal shear and moment, here you have those diagrams. And I'm going to leave the bulk of the solution on D2L for you to investigate if you want. But just right now in class, I want to talk about one location, all right? So let's think about if we can use these shear and moment diagrams to relate it to what we developed in those influence lines, specifically for shear at B, okay? So shear at B is the location of interest. That value X, right, in the brackets of the unit load or of the influence line designation represents the placement of the unit load. All right, so when the unit load is at 10 feet or when X is equal to 10, what is the internal shear at B? You're looking right at it, right? Here's your shear diagram. This shear diagram is specifically for this load case, right? The load isn't moving, it's not changing for this shear diagram. So the shear at B, when the unit load is at 10 feet, is negative 0.33. That does match up with what we found when we developed that influence line, right? So just going back a couple pages. No, that's the wrong direction. All right, so when that unit load was at 10 feet, we found the shear at B is negative 0.33 kips per kip using statics. So let's skip ahead then when the unit load is at the free end, all right? What is the shear at B?
Minus 3.33.
Right, also minus 0.33. And that's also consistent with what we found, right? So when we plotted those, right, we got negative 0.33 when the unit load is at 10. We also had negative 0.33 when the unit load was at the free end. All right, so now let's zoom in on when the unit load is at the location of interest, right? When the unit load is at B, what is the shear at B? It's discontinuous, right? Because the shear is happily at 0.33 as you make your way along the length of the beam until right before that unit load. That unit load jumps it down to negative 0.67, and then immediately after the unit load, that segment of the beam has a shear value of negative 0.67 all the way to the support at C. So the reason I'm focusing on this is because it tends to be a little bit counterintuitive when you try to map it to the influence line. And I'll show you why on the next page, which will be the solution part of this document on D2L. So when the unit load is at B, all right, this shear diagram is representing that discontinuity caused by that unit load. So if we think about when the unit load is immediately before B, all right, that's going to be where the shear at B is negative 0.67. And that's why this is a little bit counterintuitive, because I just said up until you get to that unit load, the shear is 0.33, right? But now we're taking the reverse perspective. So up until right before the unit load is at B, that's where we have this scenario down here, right? So right up until that unit load exists, right? If that unit load is immediately after B, then the shear at B will be positive 0.33. So this is the shear at B when the unit load is after B immediately. And then this is the shear at B when the unit load is immediately before the location of interest, B. All right, so it just kind of switches and it's a little bit confusing. But that's the explanation behind it. If you draw the shear and moment diagrams, you can map those values appropriately. You just have to think about it in terms of where is the location of interest with respect to the unit load, right? All right, so, and then as a recap, right, here's the slide from the last lecture where we list some comparisons between the internal force diagrams and influence lines. So this can be helpful for you to reference if you go through and start trying to, sort all of this out in your head. And now we're going to continue to focus on shear just because it is the more complex aspect of developing influence lines. And specifically, I want to think about how to draw the influence line for shear at a support. Shear at a support is not really a realistic response to be concerned about because, immediately at a support, it's really just going to be either you have to think about immediately before the support or immediately after the support, right, internally. So similar to how we have to place the unit load immediately before and immediately after the location of interest, if that location of interest happens to be at a support, then we have to specify whether the response we are drawing an influence line for is immediately before the support or immediately after the support. And there are going to be two separate influence lines for those two locations, right? Because they're two separate locations on the length of the beam for a location of interest. So first we will think about the case where shear is immediately before the support at B. All right, so I'll say this is for shear immediately before B. We're going to call that response VB minus, the minus sign indicating before B. So that means we're going to cut the beam right before the support for our statics calcs. All right, so first we will need to know the influence line for at least one of the reactions, and we have that already, right? This is the same beam configuration that we looked at before. I think I just have different notations here, right? Because I previously called the reaction the roller support at I've previously called that C and this D in the previous example. So just keep that in mind, I guess. But here, we need to identify the key locations. So for shear immediately before the support, what are those key locations? Where should we consider evaluating the response at B due to a unit load being placed? Or I should say, where should we place the unit load in order to evaluate the responses that we need to develop the influence line?
A, B, and C.
Right. Well, close. Definitely A and C, right? Because those are free ends, free end and a support. And then for B, it's going to be right immediately before the location of interest and immediately after. So you're correct with A, B, and C, but we also have to add immediately before the cut, right? So I'm going to say A, B, and C, and then also B minus. All right, so the support at B counts as the location immediately after the support, or after the cut, right? And then this is immediately before the cut. So we'll list our key locations. I'm going to list them in the order of left to right. So B minus, then B, then C. For A and B, right, we know from observation that the shear at our location of interest is going to be 0 because those are supports. So that just leaves 2 locations that we need to apply statics for. All right, so here I've already pre-cut the beam and taken the left side of the cut. So here is going to be for the shear immediately before B when the unit load is immediately before the cut. From this, or I should say from the previous influence line, right, for the reaction at A, or just from your knowledge, right, the reaction at A is not sensitive to the influence, the location of the unit load being immediately before, immediately after a given point, right? So that hairline difference is only relevant for shear. For reaction, that's just going to be, the reaction at A is equal to 0. It's going to be the same as if the unit load is at B, okay? And so we'll use the reaction at A is 0 from the previous influence line. And so from statics, right, we have our unit load. I'll sketch it in red here so it stands out. We have our unit load immediately before the cut. So then from statics, we find that the shear at B right before the support is equal to -1. So notice, right, you always want to stick with the positive sign convention when you draw your shear in moment exposed at a location. So remember your shear positive sign convention for mechanics is down on the right side of a segment and up on the left side of a segment. All right, so for the next point then, we'll say this is the shear immediately before the support at B when the unit load is at C. Now the unit load is not on this side of the cut, right? So we could, if we wanted to, use the other side of the cut, right? We could use this segment and then we would need to incorporate the reaction at B for the unit load at C. But we can also use this side of the cut, right? So we have the unit load at C, but that's not going to show up on our left side of the cut free body diagram. So we need to update the reaction at A for this value. And from our previous influence line, when the unit load was at the free end, the reaction at A was -0.33. All right, so then from statics, we sum forces in Y. We get the shear immediately before the support is -0.33. So then we plot our values. We have 0 at A and B, the supports. And then immediately before the support, we have -1. And then at C, we have -0.33. And then we connect those points with straight line segments. All right, so that's your influence line for shear immediately before the support at B. Any questions? I know this topic is not the most fun to start going through. It will get more interesting, I promise, especially when we get into the Mueller-Breslau principle. And then on Friday when we start applying it, it'll be a little bit more meaningful. So let's continue with this example and look at what we would have if we are considering, if we change the location of interest, all right? So if you change the location of interest, you have to draw a completely new influence line. So now we're moving that to immediately after the support at B. So now our key locations all right, we're still going to have the supports, right, A and B, because now we're cutting the beam immediately after the support. So in addition to being a support, this location B also counts as immediately before the cut. And then we also have to apply that unit load immediately after the cut, right? And then, of course, at the free end. So we'll say A, B, B plus, and C are now the locations of interest. That's B, right? And then B plus is after the cut. All right. So let's take a cut immediately after B. And the nice thing about this location, right, if we just use the right side of the cut, that's going to be a very easy statics calculation. We don't have to worry about the reactions at A or B for the entire development of this influence line, right? You can, if you want to, right, you can use the left side of the cut, and then you'd have to know both of the reactions at A and B for for all of these key locations for the unit load. But let's take a look at the right side. All right, so first of all, we'll have our exposed internal shear and moment, drawing them in the positive directions. We'll call that VB plus and MB. And let's think about these key locations, right? We know that at A, the influence line will be 0. At B, the influence line value will also be 0. And so the only places that we need to think about with regard to statics is placing that unit load immediately after the cut and at the free end C. So when the unit load is immediately after the cut, right, this is easy. VB plus is equal to 1. And then when the unit load is at C, also 1. All right, so this is important. For any unit load located to the left of the cut, the shear at our location of interest will be 0, right? So we have 0 all the way from A to B, and then it jumps to 1, and it's constant at 1 to the end of the beam. Now you can verify this if you want to practice using the left side of the cut. It'll be more work, but you'll reference the reactions at A and B as the unit load changes position, right? And what you'll find is that, right, when the unit load is at A, your reaction here is 1, your reaction there is 1, your reaction here is 0, right? And so what you'll find is that the two reactions will always sum to 1 for unit load between those 2 points. And so the result of your free body diagram when that unit load is acting downward and you have a summation of 1 acting upward, it's going to be 0, right, when you sum forces in Y. All right, questions? Now, I highly encourage you just to, to get your head straight with influence lines. It's just practice as much as you can. And I'm providing a bunch of example problems and practice problems on D2L for you to go through. So I highly recommend you go through them. Here's one that's on D2L. This is an example using influence lines for a beam with a hinge. All right, so the only difference is that now you have a hinge that adds a location of interest, or that adds a key location for placing the unit load. And then, you already know how to apply statics to a beam with a hinge. You know how to determine internal forces for a beam with a hinge if it's determinate, right? And you just kind of go through that process to develop influence lines. Here's another set of practice problems. I believe the solutions are provided in a separate document for this one. So I encourage you to go through these. These are a little bit simpler, right? Simpler than the beam with the hinge example, but some basic practice problems for you to kind of go through, more similar to what we did in the in-class example. And since we have a little bit of time left in class today, I would like to ask you to consider this one right here, since we haven't yet thought about a beam that has a fixed support on it, right? And so take a few minutes and think about what the influence line would be, or work through it, right? Go through the process, identify the key locations for the reaction at A, right? And then we'll skip shear at A. I'll talk about it after we discuss. So think about the reaction at A and think about the moment at B. Feel free to discuss amongst yourselves and talk to each other if you want. if you have any questions as you're thinking through this, feel free to ask too. It's not a quiz.
Yeah, I was just thinking about it. Do we need to find the influence line for the moment at A to find the moment at B?
So, no, you don't for this problem. There's a way to figure it out without thinking about the moment at A. So remember, kind of along those lines, for the moment at B, you're going to make a cut at B, right? You can use either side of the cut to get the internal force value, right? If you use the right side, you don't need to know the moment at A. All right, anybody figure it out for the reaction at A? You think you got it? Yeah? Do you want to draw it?
No?
Anyone else? Brave soul, huh?
I was just gonna say, I think it's just like 1 all the way across.
Yeah, it's going to be 1 all the way across, right? So reaction at A is pretty easy. It's going to be 1, well, I don't know why I drew it down there. It's going to be 1 all the way across, not going to change, right? Now, this is also going to be the same influence line that applies to shear at A, okay? So if you think about the shear at A, you're cutting the beam, at A, it's a support, so you have to think about cutting the beam or specifying if it's immediately before or immediately after the support, which I didn't do in the problem statement, but it would have to be immediately after the support at A, right? Because immediately before, there is no beam. So if you cut the beam immediately after A, and then placing the unit load immediately before and immediately after the cut, immediately before it's going to be 0, right? So shear influence line would technically have a point down here at 0, and then it would jump to a point up here immediately after the cut. But then the rest would be the same. it would be 1 all the way through, right? So we can think of that blue line as the shear at A. And the red is the reaction at A. Now how about the moment at B? What's that one gonna look like?
0 if the load's still left of B.
That's correct, yep. So when the unit load is at the support, it will of course be 0. And then the next key location is at B, right? And so at B, if the unit load is at B, the moment at B will be 0 if the unit load is at B, right? And I know that isn't immediately obvious or intuitive, but it will be 0 all the way from A to B. And then what's the next key location? It's gotta be C, the free end, right? So what's the value of the moment at B when the unit load is at C? Right, -15. So your influence line is gonna be like this. That should be just a 0 line. All right, 0, and then, should have just left my original line. So if you think about it, right, intuitively, if you have a unit load anywhere between A and B, it's not gonna cause any flexure at B, right? Point B will still displace, it will be pushed downward, but from that point on, you're just gonna have a straight line displaced shape, right? Your only flexure is gonna be between A and wherever the unit load is. Once that unit load is after point B, then point B is included in the portion of the beam that's gonna experience flexure. So at that point, you're gonna have an internal moment up to a maximum value when the unit load is at the free end, right? All right, any questions on this process? Okay, so I want to give a little bit of extra credit for those that showed up today. So I think I've got everyone's name here. It's Michael, Ian, no, sorry, you're Ian. Okay, Ian and Blaine, yes, sorry, Blaine, Tony, Noah, Owen, Porter, Stephen, Claire, Trevor, Cade, Braxton, and Nathan, thank you. Okay. All right. I was close to getting everybody. Nathan. All right. Well, thank you all. And I will see you on Friday for more influence lines.
I know it's too bad. No. We're supposed to be like this big. Yeah.
Hey, you can make the.
Bye. Yep. See you.
First one was so bad. Yeah, no, that's what Brad's doing.